All right, guys, we are starting on this page in your packet, the comparing two means. Right, I have an extra one. Oh, yeah. All right, guys. So we are doing all of this stuff with means today. Ready, guys? All right, last time or 2 times ago, we did the notes on the proportions, and then we did practice problems on that. Yeah.
The quizzes do the 6?
Yes. So next Monday, your quiz will be due. Next week's kind of weird. The 6th is when that's due, and we'll grade data journals, but then the 8th is a religious observance day, so I can't give you your test then. So your test isn't until the 10th. So the 8th, we can just do practice problems together in class. It's just kind of like a bonus review day for you guys. Okay, so today we'll finish the notes. We'll do practice next class. I'll give you data journals then, and you'll have time to work on those too, okay? So today will be lots of notes, though. All right, so we're doing difference of means now, but let's look back at when we just had our one sample, what we did before. We'll do this off to the side. When you were doing sampling distributions, you had mu of x bar, which was equal to mu, and we had sigma of x bar, which was equal to sigma over n. Okay? Square root of that. Sorry. Now when we're doing difference of means, it just means we have 2 populations that we're looking at. So you have 2 mu's that you're subtracting. You have 2 sigmas to deal with. Something to note in your standard deviation formula, whether we're adding or subtracting, looking at anything with our means, even if it's a subtraction, this is always a plus. Okay, you're always going to add the variances and then take the square root of them to get the standard deviation. You can't just add the standard deviations. All right. That's what this little bullet point is talking about. You can't add the standard deviations, add the variances, and then take the square root. And this is on your formula sheet. So let's do this little example here. The AP test is 2 parts, each normally distributed. Part 1, we've got it's normally distributed with a mean of 25, a standard deviation of 6. In the second part, mean of 20, standard deviation of 7. Describe the distribution of the combined score for part 1 and part 2. So that just means you'd be looking at the mu of part 1 plus part 2, which would be the mu of part 1 plus the mu of part 2. It seems like common sense, I know, but that's what that is. So in this case, that'd be 20 plus 25, or 25 plus 20, write it in the right order. So if you were to combine the 2 parts, that distribution would be centered at 45, okay? But to find the standard deviation of this combined distribution, you can't just add the 6 and the 7. You have to do, excuse me, the standard deviation of the first one squared, and then standard deviation of the second one squared, both of those over n. Sorry, squeezing this in here. We'll go sideways. So our first standard deviation was 6, so I'd do 6 squared. We don't really have a sample size, so we're going to say it's one test is what we're looking at. And then the other standard deviation was 7. And so we get a lovely square root, let's see, 36 plus 49. The square root of 85 is your actual standard deviation of that distribution. Does that make sense? The whole point of that is just to show you, you can't just add the standard deviations together. You add the variances together and then take the square root to get the standard deviation, okay? Okay, then sometimes we had standard deviation sigma unknown. And again, back to just looking at that with our one sample. We had standard error, which was S over square root of n. And our degrees of freedom was always n minus 1. Again, if we're dealing with two populations here, it looks a lot like adding the variances together, but we don't know sigma, we only have S, so that's the formula we follow. And then the degrees of freedom part, this is a little different. It's a very complicated formula, so either your calculator's going to tell you what your degrees of freedom were, or if you have to state it somewhere in the problem, you pick the smaller of the two. Sorry, question?
Yeah, I just forgot. What is that stand for?
Oh, standard error.
Oh.
Yep.
What is it?
Standard error?
Did we do that before?
Yeah, we did that, oh, like unit 2, maybe? 2, 3 combined? No. Yeah. Degrees of freedom? Yeah, the DF. So again, your calculator now, when you're dealing with two populations, will tell you degrees of freedom. Or if you must pick a number for it, whichever sample size is smaller, you use the degrees of freedom from that. Okay. All right, conditions. There's really no change here from what we were doing before as far as normality and the simple random sample. You just have to check your conditions for both populations. So both the sample sizes have to be greater than or equal to 30. That's your central limit theorem. You may have been told both populations were normally distributed. Or do you guys know what number 3 means? Both NPPs approximately linear? Good. Yeah, the normal probability plot is approximately linear. We don't use it a lot, so I know it's easy to forget like where that even is. It's something you can grab. Simple random samples the same. Independent samples, we talked about that when we did proportions. Definitely adding that one in. The 10% rule, still not going to make you write it out. Recognize that you will see it on Khan Academy for some. So the big thing is just you have to check for both populations. It's tedious. Think of it as free points, though. All right, guys, when you're ready, turn the page. Now, these are all the things you can do with your means problems with two populations. We've got confidence intervals, hypothesis tests with sigma known, sigma unknown. all that good stuff. So we'll just do reminders of what you did when it was one population over here on the left. So if you had a confidence interval, you did X bar plus or minus Z crit times sigma over, that is not sigma, sorry, I've been writing lots of thetas today. Sigma over square root of n. What we're doing this unit, you now have two populations that you're dealing with, so you're going to find the difference between the two X bars. And then again, with the sigma, remember we can't just subtract, you don't ever subtract them. You're going to add your variances, and that's your new piece of that formula there, okay? All right. When you were doing a hypothesis test, remember we would find a z value. We had a formula for this, x bar minus mu over sigma over square root of n. Hopefully that's familiar. That is when you knew sigma, you could do a z test. And we wanted to just call it a z-test in that unit. And I would say it's a one sample z-test. I think now you can see we've got so many different pieces going on. You need to identify, is it a one sample? Is it a two sample? Is it means? Is it proportions? You need to tell me the name of whatever it is that you're doing, okay? All right, we also have a hypothesis test if sigma is unknown. What does that mean if we don't know sigma? What are we talking about then? Yeah, the t-test, okay? We've got to use your t-test at that point. So when we just had one sample, you had, and sorry, we're doing the confidence interval first. X bar plus or minus, you had a t crit instead of a z. And then it was times s over square root of n instead of sigma over square root of n. And then same thing with the hypothesis test. If sigma is unknown, instead of finding a z, we find a t value. With one sample, it was just x bar minus mu over s over square root of n. Does it feel like a lot? Yeah. Hopefully it's repetitive. Hopefully you're seeing those same things popping up. The note at the bottom there, sometimes you'll be told the two individual x bars or mu's. Sometimes you'll just be told what the difference is between them, and that's okay. It's whichever way the information is given to you is how you have to proceed through the problem. They both work. All right, we'll talk about matched pairs and then we'll do one, okay? So turn the page when you're ready. So instead of like listing like mu sub 1 is 10 and mu sub 2 is 8, sometimes you'll just be given, and that's okay. So like in your problem, like you can see, you know, we've got that value. Instead of listing the 10 and the 8, you can just list the 2. Does that make sense?
Yeah.
Okay.
So we put it into the formula.
Yes. Yep, exactly. All right, guys, we're not going to write anything on this page. We're just going to look through a matched pairs T. So this gets used if you have people that are almost identical or the same person testing two different things, like, I don't know, two different running shoes, and you wear one on your right foot and one on your left foot and check the durability, that sort of thing. Like, you have to have the people involved being very similar to look at the results. Before and afters, that sort of thing. Talking about the, you know, the durability of gloves there, shoes or gloves, you wear one on one hand, one on the other. They should go through the same conditions because one person is wearing those, okay? Does that make sense, how that's got to work? It can't be, you know, you who live in Alaska and you who live in Florida are testing a pair of winter gloves. Like, that doesn't make sense, okay? You end up with something that is just like a one sample test. Because what you're going to do is find the difference between either a pre and a post, or whatever the ranking system was used for durability, that sort of thing. You're going to have one mu of the difference that you're looking at, okay? So it goes in this unit because it is definitely two things that you start with, two different populations, if you will, but you perform it as if we're back in the previous unit, okay? So we'll do one of those examples at the end. Hopefully we'll get there. But it's, you know, everything else is the same as far as doing the test. Your conditions are the same as the one population, degrees of freedom are the same, all of that stuff, okay? All right, let's try some of the basic mean stuff first and see if we can get through some of those. All right, we're going to slightly change our examples here too. So go ahead and find this page. It's a couple pages past where we were. We're going to do a slight edit here. So instead of boys' heights, we'll say basketball player heights. So those are distributed normally, mean of 67, standard deviation of 3, and instead of girls, we'll say swim. Well, but basketball and baseball aren't the same season, so they couldn't be independent. Well, that's good. Baseball's great. Make it fun for you. I'm going to go swimmers. Sorry, guys. Both winter sports. They should be independent. We're not talking summer swim here, okay? All right, so we've got those distributed normally, mean of 65, standard deviation of 3. Okay. So this is a sampling distribution problem. We have a random sample of 10 basketball players and 15 swimmers. So what's the probability that the basketball players are at least 3 inches taller than the swimmers on average? Felt like my examples were a little outdated with the boys and girls being our two separate groups. So we'll change it to basketball players and swimmers, okay? All right. First thing we have to do is define what we're even talking about. I've told you it's a means problem, so we're going to look at mu sub b and mu sub s. Okay, those are like our two groups. What are they, though? What is mu sub b? What am I talking about? Yes. The true, you can say true, I like that. The true mean height of JMHS basketball players. And feel free to abbreviate what you need to, okay? So what does that make mu of S? There you go. The true mean height of JMHS swimmers. All right, so we've defined who we're talking about here. Let's list out everything we know. What is mu sub B?
67 inches.
Good. And sigma? 3 inches, good. And what was our sample size? 10, nice, okay. And then same thing for the swimmers. What's the mu of the swimmer heights?
65.
Yep. 65. What's sigma of swimmers? Also 3. And then sample size? 15, okay. What do you think we have to do next for both? Condition, okay. All right, normality. How do we know this is a normally distributed distribution? Why do we know that? Yeah. It's not, no, so we can't. No, something else was said. Yes, they just stated it, which is lovely. Because we couldn't really make a normal probability plot out of this. We don't have any data to actually do that, so thankfully it was stated. We are told population is normally distributed. Okay, what about random? Stated, yep. Okay, and then we have our new one, independent. Okay. Yeah, so you can't technically play 2 winter sports, right? Okay. So yes, can't be in both groups. So when I do the conditions for the swimmers, oh yeah, go ahead. So if it can muddy your results, if you're counting the same people in both groups, but then we're talking about the difference in the heights of these 2 groups, and you're like, well, I used the same people in both. It just gets a little questionable there. So you want 2 completely independent groups, and then we can make comparisons about those groups.
For independent, is that like the only thing you'll ever say?
Pretty much, yeah. Yep. Yeah.
Well, basketball plays is slightly independent because you can play both these sports and actually you didn't play in the same season.
On the same season.
Not in the same season.
But
You can't be a JMHS swimmer and a JMHS
Are they
basketball player.
rules that are they actually rules like that?
I believe so, yes. Yeah.
You also can't try out for sports, so
Yeah,
you can't be a
it wouldn't work.
But you can't try out for
Okay. So guys, when we do the conditions for the swimmers, what do you think? Are they pretty much going to be exactly the same? Yes. Is it annoying that you have to write it twice? Yes. You'll do it anyway, though, okay? So normal, because they said the population is normally distributed. Random was stated. Independent. Yes. waters. Okay, so that's just all the stuff you have to do before we actually get into the sampling distribution part of it. Okay? All right, so let's look at mu of basketball player heights minus swimmer heights. Okay, because the question asked us, what is the probability that the boys are, or I'm sorry, that the basketball players are at least 3 inches taller than the swimmers on average? Okay, so we're finding the difference in the heights of these two groups. So that's why I'm doing mu of basketball minus swimmer. Now, could I do swimmer minus basketball? Yeah, you would just have the opposite sign in your answer. Okay, that's all right. You just have to be able to interpret that correctly. All right, so if I'm doing the mu of the difference here, I need to look at the mu of the basketball players minus the mu of the swimmers. So what was the mu of the basketball players? 67 minus, what was the mu of the swimmers? 65. So we end up with the difference, the mu of the difference being 2. All right, we also need sigma of that difference. Okay, so remember, I don't just subtract the 2 sigmas. My formula is going to be sigma squared of the basketball players over the sample of the basketball players plus sigma squared of the swimmers over the sample size of the swimmers. All right, so what was the sigma for both groups? Yeah, both 3. What was the sample size for the basketball players? Good, and then 3 squared over sample size for swimmers? 15. All right, so get out your calculators, guys. What does this come out to? 1.22, good. Now you could actually find the z-score that goes with this and then do your normal CDF and all of that from the z-score, but you don't have to. You can just use this information since we have the mu of the difference and the sigma of the difference. So I'm going to draw a picture first. Okay, since the mu of the difference was 2, that means our distribution is centered at 2. Now, what was the question asking us? How likely is what?
What is the probability that the basketball players are at least 3 inches taller than the swimmer?
Yeah, so we're saying what's the probability that the difference is actually 3 inches instead of 2? Well, 3 inches would be somewhere over here. And then I want to know, at least 3 inches taller. So I'm talking about that part. You are now going to do normal CDF. We're going to go from 3 to infinity. This was centered at 2 because that was the mu of basketball minus swimmer. And then your sigma is 1.22, which is sigma of basketball minus swimmer. So go ahead and calculate that. What do we get? Did you do 3 to infinity or did you do negative infinity to 3?
Yeah.
Okay, I was like, you got the opposite part. Okay, I'll just say 0.21, but yes. Anybody calculator troubles? All right. Okay, so now we have to write our contextual conclusion, actually answering the question they asked. So we would say what this 0.21 is telling you is how likely it is for this to happen. So we'd say there is about a 21% chance that simple random samples of 10 basketball players and 15 swimmers at JMHS will result in the basketball players being at least 3 inches taller than the swimmers. On average. Okay. Take a minute, process that. That's what a sampling distribution problem looks like when you're dealing with the difference of means. Questions? Anything at all, Brad? I think sometimes it's hard for you to identify that it is a sampling distribution problem. Just recognize that the confidence interval ones will actually say construct a confidence interval. So those are the easiest ones to identify. The hypothesis test is going to ask you something about evidence, like is there enough evidence for this? If you don't see either of those, it's very likely you have a sampling distribution problem, okay? All right, guys, turn the page when you're ready. Okay, we're gonna do a t-interval this time for means. So again, we're changing the problem. So sticking with boys are basketball players, change that. And change girls to swimmers.
What's wrong with this?
You what? Okay. All right. So just like we do with pretty much every problem, we have to identify the mu that we're talking about. So we're going to have mu sub b again and mu sub s.
Are we just keeping the conditions on that stuff from the last couple?
Well, are they the same?
Oh,
They're not exactly the same. I know. We will be able to keep it from this 2 sample 1 down here to this hypothesis test. So that helps us a little bit. But they are slightly different. All right, so mu sub b this time we know is the mean height or the true mean height of basketball players at Langley. And then mu sub s is the mean, true mean height. So it's mean of Langley swimmers. Right. And then let's write out everything we know. Do we know mu sub b this time? Do we know the true mean? No, we don't. What do we know? Yeah, we just have the sample that we're working with, right? So we don't know mu sub b, and we don't know sigma sub b. We do know x bar. And that was, what, 66.9? We know S of this group is 3.08. And we know our sample size, which was 55 basketball players.
Oh,
You guys good?
Just to be sure, like,
Yeah.
the last question was about, the question told us the population, this one's telling the example.
Yep, exactly. All right, then for the swimmers, again, mu sub s, we don't know. Sigma sub s, we don't know. But x bar sub s, we know it was 64.3. What'd you say? Sorry. Oh, I mean, it's fair. I don't know why we have so many basketball players and swimmers, but it's a lot of basketball players and swimmers at Langley. This is what happens when I edit the example in the middle. But. All right, then we have our S sub S, which was 3.15, and our sample size for this group was 45. We okay with all of that information? Okay. What do we have to do next? Conditions, okay. Okay, so we start with normality. Why do we know this is normally distributed this time? Yeah, go ahead. What'd you say? Yes, this time our sample size is actually large enough. So our sample size was 55, which is greater than or equal to 30. So by the central limit theorem, this is normally distributed. All right, what about random given to us, right? They stated it. And then are two groups independent? Yes. Cannot be in both groups. So when you go over to the swimmer conditions, they're the same except the sample size was 45, but it works out the exact same way. So normal, sample size was 45, which is greater than or equal to 30. So CLT. independent. Yes, cannot be in both groups. Okay. I've run out of room, but clearly we're not done with our confidence interval. That's just the beginning part of the process. It's all the stuff we gotta check before we do anything. Any questions so far? Okay. We're gonna write out the formula, but we're gonna do this on our calculator, okay? So I'll move over here where I have a little more room. So they're asking for a 95% confidence interval. So the formula would be the mean, your X bar of the basketball players minus the X bar of the swimmers, plus or minus. Everybody okay with why this is a critical T and not a Z type of interval? Yeah, we didn't know sigma, right? We only had S, so we have to use the T. And then the rest of your formula, it would be S of the basketball players squared over that sample size plus S sub S squared over that sample size. Now again, I'm not going to have you key that in by hand. Let's go ahead and use your calculator. Let me get mine open. All right, where do you think I go? All right, are we doing a test or an interval? Interval, right? So I'm going to go past the test here. It's not a Z. It's not just a T because we've got two samples happening. You guys see two sample T interval?
Yeah.
Okay, that's the one I want you to pick. 0. Okay, then you have the choice of inputting data or statistics. Data is if you actually have the individual lists, like if we had all the heights from each group. We do not. So we can go to stats, and then you can put in the information we actually have. So X bar of the first group was 66.9. And that standard deviation was 3.08. Sample standard deviation, that is. Sample size there was 55. And then the second group, which was 64.3 for the X bar. S of the swimmers was 3.15. Sample size of that group was 45. So pooled, we only deal with pooled right now. We dealt with it with our proportions, but it's if the two are set equal to each other or if the difference is going to be 0. You're almost always going to pick not pooled when we're doing the T stuff, okay? So we're not going to pool here. Then we can calculate. All right, are you getting 1.36 to 3.84? Yeah, okay.
So it's always going to be a pool.
I won't say always. For right now, for these problems, yes. All right, anybody calculator troubles on, did it not work on yours?
then she just don't understand it. I calculated that, so. So if it's.
Yep. Okay. So this came out to be roughly 1.36 to 3.84. So that's your actual confidence interval, and then we have to write our contextual conclusion with that. So we'd say we are 95% confident that what? What were we even talking about in this problem? Yeah, go ahead. You're okay. How about we say that the true mean difference in heights? Yes, there we go.
Should we write this in like
Yeah, so we're saying, because you only have the sample information, you're trying to not guess, but you're saying we think the true mean and the difference between these two groups' heights is somewhere between 1.36 inches and 3.84 inches. If we knew the populations and knew mu of the basketball players, mu of the swimmers, we wouldn't have to make an interval, right? If you know the mu's, you can just subtract them and then you have that. But when you only have samples, that's when you create the confidence interval. And you're trying to narrow down, like, we think the truth is somewhere in here.
Should we learn it like under the base of the.
Oh, no, that's a second part. Yeah, sorry, I didn't realize what you're asking. You were getting much more of an explanation there than you wanted. So the true mean difference for heights, or in heights, of basketball players and swimmers at Langley is between 1.36 inches and 3.84 inches. So that part, it's very similar to what we did in our confidence intervals before, okay? Questions so far? 2 examples to go, guys. We can do this, okay? Hang in there. Do you see now why I didn't want to do this the day before Thanksgiving? I think you might have all just walked out on me. I don't know. All right, so the next one, it says, based on the sample data from the previous question, is there significant evidence? So that's like your key to go, oh, I'm doing a hypothesis test. They're talking about evidence and they're giving me an alpha level. They're looking to know if there's evidence to suggest that the difference in heights between basketball players and swimmers at Langley is different than it is at Madison. Okay, so we're trying to decide, is this difference in heights consistent between the two schools, or is it different from one to the other?
So are we using data from both the first two?
Yes. All right, so what we're going to do here, everybody get why this is a hypothesis test? Think that makes sense? Okay. It is called a two-sample t-test for means. Are we okay with why it's a t-test and not a z-test? Okay, so when we were going through this problem up here, the confidence interval one, did we know sigma in that part of the problem? No, okay? If we don't know sigma for part of it, we have to do the t-test. Okay? All right. Now, the happy news here is we've already checked conditions for both of these groups. We don't need to do that again. So we're just going to jump right into the actual hypothesis test part. What's something you have to write every time you do a hypothesis test? Yeah, we have to write like the null and alternative, correct? Okay, so let's think about the null and the alternative. All right, we are still talking about the difference between the heights of the basketball players and swimmers. So we're still talking about mu sub b minus mu sub s. Okay, the question says, is there evidence that this difference is the same between Langley and Madison or different between Langley and Madison? Do we know the difference in heights at Madison? That one we knew, right? When we did our sampling distribution, wasn't this dealing with the actual population here? Like we knew mu sub b and mu sub s, right? What was the difference between mu sub b and mu sub s at Madison? 2 inches. So we want to know, is the difference still 2 now that we're talking about the Langley students here, okay? So we want to know, is the difference 2? That's our null. We're saying the difference in height is 2. What do you think our alternative is going to be? Not 2. So what does that make this? Like, what's unique about this test? Two-tailed, yes. Okay. We're going to write out our formula for this. It's not a small formula when we're doing the t statistic here. It is x bar sub b minus x bar sub s. So you always start with your sample minus the parameter. So mu sub b minus mu sub s over square root of, we don't have sigma, we have s instead, so s sub b squared over n sub b plus, always plus, s sub s squared over n sub s. Okay, now I would love to tell you that we're going to just do this all on our calculator and do the test there, but we're not. So let me just show you on my calculator why it won't work. I know it's disappointing. So if I go into the test here, and I do 2 sample t-test, and I go and put this information in, it all looks great. But then the issue is with your null and alternative. When you're doing it on your calculator, it's always starting with that the null is the difference is 0. Is our null that the difference between the 2 heights is 0? No, we're saying it's 2. We can't change that on here. So we can't use it for this part of it, okay? What that means is we get the exciting task of putting in all of these numbers. All right, so we know what all of the pieces are. So x bar sub b, we had it up above, was 66.9, minus the swimmer average is 64.3, minus the mu. We know the difference that we're talking about here is 2, right? Mu sub b minus mu sub s. Yeah, okay. Over square root. So the S for basketball players was 3.08 squared. Over that sample size was what, 55? Plus the 3.15 squared over 45. Okay. Key it all in at once, guys. Use the fraction key on your calculator. See what you get. Try. Look at you all trying. Some of you are not. There we go. And you guys know, like, the shortcut to the fraction key? Yeah? No? Okay. I'll show you that. Yep. It's a handy one. So if you ever need a fraction, just do alpha y equals, and the first thing that pops up is your fraction. Okay. And then put another fraction in there. Okay, so guys, you can key it in nicely, like that. Did we get there? Oh, not 445.
Got error.
You got error. Okay, let's see what I get. Ooh, yay, that's right. All right. You should be getting 0.957. You're not getting that one. Well, in theory, you can.
How? Is it really simple? Yeah, you can do it.
I don't think you can do it. 9 minus. Get there? Yeah.
Yes.
No, okay.
Yeah.
Yeah.
Good. You survived.
Well, that means it's very possible. Wait, no, that's.
But we didn't get the p value.
I don't know.
Did you get it?
I accidentally did 2 decimal points.
That will mess it up. All right, so over here I'm going to write 0.957. This is a point where I think a lot of you are like, okay, I can do that, and then you aren't really sure what to do with that number. Is that correct? Like you're kind of here and you're like, oh, shoot, now what? That is what goes in your picture. So I'm going to draw my lovely distribution here. Because we did all of that work, it is now centered at 0. Okay? And then I've got 0.957. So, okay, somewhere over here. But what did we say about this test? Two-tailed. So what else do I need to do? I need the other tails, right? Yeah, so I need the negative 0.957. And then you need to figure out how to find the area of the shaded part. You can't do both of them at the same time, but they're going to be congruent. So if you find one tail, you just double that answer, and that's the p-value that we're looking for. So how do I find the area of one of the tails? What do I use? We used normal CDF on the other one, but this isn't a Z distribution. So what do you think? Yes, there is a TCDF, guys. Yeah. So I'm going to do the positive one just because that seems easier to me and I don't have a negative to deal with. So 0.957 to infinity. And then,
My mom's gonna have a concussion appointment.
oh, did you have a pass?
Not yet, but she says I have to leave at 2:30.
Did she? I mean, just go. I don't know, but you're supposed to have a pass. So
Okay.
I'll email attendance and tell them. But
Okay.
did you turn in a note earlier today?
No, she's checking. Or she is checking it out.
Yay. Have fun.
Thank you.
Now, guys, find your TCDF on your calculator. Do you know where it is? It's under norm CDF. Yes. Okay. What else do they ask you for here? Degrees of freedom. Okay. We said degrees of freedom was really complicated, but if you must, what do we do? Of which one? We have two ends. The smaller one. So what is our degrees of freedom in this one? 44. All right. So what do I get? 0.17. And remember, what we're doing here, all of this TCDF, this is giving you your p-value. Okay? It's two-tailed, so it's not just 0.17. What do I do? Yep, so it's 0.34. Okay, you have to double it. So, what do I conclude then? My p-value is 0.34. What does that mean? Fail to reject. Excellent. So, it's pretty big, yeah. Since our p-value of 0.34 is greater than alpha of 0.05, we fail to reject the null. There's not enough evidence to suggest that the mean difference in heights of basketball players and swimmers at Langley is different than at Madison. Nice, lengthy conclusion. Okay. But again, it's a lot of things that you already know. Okay. A lot of it with these problems is making sure you sort of don't lose your focus. Like, it's easy to get kind of in the middle of the work and then stop and go, what am I doing? Like, where was this problem going? So Stop. Read it. Yeah, yeah, it happens. Take a minute. Read it. Okay, guys, you're doing good. We have one left. You can do it. I think you'll like this one. Matched pairs, because you go back to only having to check conditions on one group, so you'll feel good about that. Yes. Yeah. Yeah, so independence is not one of our conditions with this. It's like we're back in, what was it, Unit 4, and we didn't have that condition. They're clearly not independent. Yeah, exactly. So you are correct. All right, guys, matched pairs t-test. Okay. We're going to look at this one. We've got Mr. Grossman wants to know if his lessons actually help his students learn math. So we decided to give a pre-test before the unit, teach them some math, and then give a post-test. Hopefully they do better, right? So we've got pre-test scores, post-test scores, and then we want to know, assuming the student scores are normally distributed for both tests and the sample of students is taken randomly, is there significant evidence to suggest that Mr. Grossman's teaching improves student scores on math tests? So again, we see significant evidence. You should go, okay, hypothesis test of some kind, right? All right. This is matched pairs because you've got the pre and the post. So what we actually care about is not these individual values. We care about the difference with these individual values. We care about delta, which means the difference. And do you think I'm going to do pre minus post or post minus pre? Yes, so that's what we're going to find is post minus pre. You could go through by hand and go, okay, 82 minus 32 is 50. Or we can have our calculator do this for us. We need it in our calculator anyway, so we might as well just let it do the work for us. So go ahead and on your calculator, go to Stat. And then we're going to pick Edit. We have to put these values in our lists. I'm just going to go ahead and do pre-test in list 1 and post-test in list 2. So go ahead and put those in. All right, so we've got our two lists in, we've got our pre and post test, but now I need to actually find the difference between those. So go ahead and go back to just like the main home screen, your blank screen here. I want to do post test minus pre test. So for me, that's list 2. So I'm going to push second and then go down here, list 2 minus list 1. And I want this stored somewhere specifically. I want these values to end up in list 3. Does that make sense? Like I want to find the difference and I want to make sure I have that list of new values. So I'm going to hit this store button over here on the left and then say list 3. So I did the second and then like 1 or 2 or 3 at the bottom. Do you see it? In blue?
Oh, yeah, yeah.
Okay. No, that's fine. Yep. Apparently I hit enter twice.
No, because we're doing post minus three.
Oh,
So I just did
oh, yeah.
backwards.
All right, you should be getting this list. Store button on the left side right above on. See it? And then store it in list 3. If you're like, I don't know what you're talking about, please come here. Just tell me. Think you got it? Did you get something kind of like this? I hit enter twice, so I have 2 lists, but no, I don't know. It just happened. Anybody struggling with this? It's fine if you are. I just want to make sure we got it now. Okay, we're going to come back to this. We got to do all the other, first stuff that we do in a hypothesis test, and then we'll come back and use this to actually calculate it. Okay, so we're going to define our mu, but this time it's just mu of delta. Okay, it's just the mean of the difference in the pre and the post test that I care about here. So mu sub delta, it's the average change in test scores, or the true mean change in test scores. That would be fine. And you can even note, like, we are doing post minus pre. Only one thing to define, and then conditions. Only conditions for one thing here. All right, so normal. What do we think? Sample size is definitely not large enough. Do I have to do a normal probability plot? It's stated, yes. Thank goodness. And then what about random? Okay. And then guys, we don't need to do independence for this one, okay?
This was a good problem to be the last one.
Right? I know. Like, we can finish with this one, yeah. All right, so we got our conditions. We now need a null and an alternative. Okay. What do you think the null is?
That's the poster.
No. It's always got to be something equal. So mu sub delta, what is it going to equal? 0. Yes. What does it mean if that equals 0? There's no change. Mr. Grossman taught them nothing. That's what that means, okay? Yeah, I think there's going to be some significant evidence, yes. All right, now the alternative. What do you think the mu of delta? Well, we want to know if his teaching was beneficial. So we don't really want not equal to, right? Just greater than, yeah. We want to know that they actually learned something. Seems like a good thing. All right. So let's go ahead and write out our formula, but then we can use our calculator on this one. So we're back to just like a one sample t type of problem here, okay? So your formula is much simpler also. It's going to be x bar of delta. We'll have a little subscript, but other than that, it's not bad. Minus mu of delta over s sub delta over square root of n sub delta. It's a lot of deltas. Yep. Oh, I wrote a lot of thetas earlier today in pre-calc honors, so I was mixing up all my Greek letters. I don't know. We're in the middle of trig proofs and like the double and half angle formulas and sum and difference. It's a little painful. So. The proofs, once you get them, they're kind of fun, but until you get them, if you never get them, it's very painful. Yeah. Oh. To squeak you through, huh? All right, guys, so what test do you think I'm picking? T-test, right? We're back to the basics here. Woo! Okay. Do I want data or do I want stats this time? Data. We rarely want data, but this time we do. Okay, but you want to make sure you put the right list in. So mu sub 0 is 0. That's good because we're talking about the difference being 0. Where is my list, though? L3. So I'm going to put L3. Frequency, we don't have anything to deal with frequency. And then I want to make sure I pick greater than. And I'm going to do draw because that'll remind me to draw a picture. Some of you forget your pictures. And then I need to write down both of these numbers. I need to write down what t equals. That's your test statistic. And then the p-value. It's not even giving you scientific notation this time. It is just flat out saying it is 0, okay? Pretty much, yeah. We can see it, yeah. So for my test statistic, I got 18.9. And then your picture, you know, it's centered at 0. Is there really anything to shade? No, there's not really anything to shade because the p-value ended up being 0. So we just need our conclusion, guys. What is it? I know we're so close. Yeah, since our p-value is so small, right? Okay. Since our p-value of 0 is less than alpha, I mean alpha of really anything, but alpha of 0.05, we reject the null. There is enough, you could say there's significant evidence, there's overwhelming significant evidence to suggest that students improve we'll just say improve, I guess you could say, or improve their score after being taught by Mr. Gross. You made it, guys, with a whopping 8 minutes to spare. Good work, guys. Yeah. I have not given it to you. I haven't copied it yet.